Alright, today we are going to continue our discussion of pressure, and specifically we're going to talk about something called Pascal's principle. So Pascal's principle tells us that if an external pressure is applied to a confined liquid or gas, a fluid, the pressure at every point within that fluid increases by the same amount. So basically what that means is if you have a confined fluid, let's say the liquid inside this tube, and I push on it on one side, the increase in pressure happens all throughout this liquid. It does not happen just at that one point that I apply the pressure. And this is a principle used for hydraulic lifts. So anytime you go and get your car fixed, they have to lift the car up off the ground to get underneath it. That is how this works. They apply a force on one end, and because that increases the pressure everywhere in the fluid, that will output a force under your car. This is also how hydraulic brakes work. When you step on your brake pedal, it's not like it compresses all of the fluid right behind the brake pedal and then that's it. The pressure in the entire system increases by the same amount. So when you push on your brakes, the pressure increases to push your brake pads against the disc attached to your wheel to slow it down. So we know that our equation for pressure is force divided by area. So if we have one area here and another area here, and we know that an increase in pressure on one of these has to be the same as an increase in pressure in the other, we can set these two equations equal to each other. So we get the force divided by the area of the initial area is equal to force divided by the area of the final area. And this is how the hydraulic lift works. It has a very small area over here, and we don't have to put very much force in, because for a large area over here, we get a much larger force if the pressure is the same. This principle can be used to measure pressure, and there are several different instruments that measure pressure. The one in this picture is called an open-tubed manometer. And what happens is this end of the tube is just open. So the pressure that it feels on this side is atmospheric pressure. The pressure of whatever you want to measure is put in on this side. So if the pressure being measured is greater than atmospheric pressure, the liquid will rise on the left side of the tube. If the pressure you're putting in over here is less than atmospheric pressure, it would fall. And using our equation of pressure is density times gravity times height, you can look at how high the level changes on this side and determine the pressure. Another instrument used to measure pressure is something called a Mercury Barometer. And what happens is you have a little bowl at the bottom and a tube that is open inside the bowl sticking out. And both of these are filled with mercury. There is a little vacuum up here, and if there wasn't a vacuum here, that would be bad news. If this were to break up here, then all is lost, because all of the mercury would come flooding out and overflow and go everywhere, and it would be a horrible mess. So we have to have that little vacuum seal at the top in order for it to work correctly. But what happens is there's 1 atmosphere of pressure pushing down all over the surface of this open bowl. And that pressure forces the liquid, or the mercury, to rise a certain amount. We know that the distance from the top of the mercury down to the top of the mercury in the bowl is 760 millimeters when the pressure is 1 atmosphere. If we were to take this Mercury barometer and go stand on Mount Everest, the atmospheric pressure would be much less because the height of the air above us is not as tall. Therefore, there's less pressure. If there's less pressure, this height, the mercury will not go up to the same height. If we were to take this and go down in a deep, 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 deep valley where the height of the air above us is much more, then the height of the mercury would increase and it would go somewhere up here. Hopefully not too much because we don't want to break anything. And it turns out any liquid can work in this barometer, but the really dense ones are convenient because that means we don't have to make our barometer gigantic. So in this picture, they have a barometer that's using water. And look at how stinking tall this thing is. In order to measure anything, it would have to be so tall because of the low density of water. So how tall would a water barometer have to be at 1 atmosphere? So if we had a water barometer here and we wanted to accurately measure 1 atmosphere, how tall would it have to be? Well, we can figure that out using our pressure equation. Pressure is equal to the density times gravity times the height. We can rearrange to solve for height, so it would be pressure divided by density times 9.8. So the pressure, remember, 1 atmosphere is 1.01 times 10 to the 5 pascals. The density of water is 1,000 kilograms per cubic meter, and we multiply that by 9.8. So in order to measure 1 atmosphere of pressure with a water barometer, the tube would have to be over 10 meters tall. That's over 30 feet tall. That's ridiculous. So we use more dense liquids in these barometers to make them more practical. If this number increases, height decreases. So the more dense, the less height you need, which is why they use mercury. Mercury is not necessarily the safest thing, which is why they don't use open mercury barometers anymore. They're not open at the bottom here because it causes health hazards, but they used to be. So your homework assignment for tonight is to research a third kind of pressure gauge. So we talked about the open tube manometer, and we talked about a mercury barometer. Your job is to research a third kind of pressure gauge and explain how it works. Talk about pressure, density, and height. And please make sure to cite your source.